All right, welcome back, students, to another week of Chemistry of Everyday Life. We will round out the lectures for this semester with this unit. And so we're going to end this unit with just talking more broadly about chemistry of things found in your home. Okay, so there's a lot of things you can talk about in this topic, so I'm just going to break it down into two categories that we'll be discussing today. The first one is going to be painkillers, pain relievers, so medicine, and the other one is soaps and detergents. Okay, so those are the two categories we'll be discussing today. At the end of the semester, you will have a chance to do your own presentations about various topics that might interest you, so including medicine and including household products. So this is just kind of like a demo almost for how you should talk about how you should discuss the things you do in your presentations. Okay. All right. So the first topic I will talk about is pain relievers. So the big fancy word for that is analgesics. And the first type of pain reliever I'll talk about are called the NSAIDs. So which stands for non-steroidal anti-inflammatory drugs. So let's break up that. So non-steroidal, so they're not steroids. That's what basically that word means, because there could be drugs that are made from steroids, hormone compounds. So we're not talking about those molecules today. So we're just talking about these non-steroidal kinds. And they're anti-inflammatory. So they fight inflammation, right? So their job is primarily to relieve pain and reduce inflammation. And it does this by blocking a production of a compound known as prostaglandins, right? And these are basically, you can think of them as pain chemicals. They are the one that send the signal to your brain, signaling you have pain somewhere in your body. And this designation is basically to distinguish these kinds of drugs from the more, like I said, the steroid drugs, which are more potent, things like the cortisone or the prednisone. So these more potent drugs you would need prescriptions for, whereas NSAIDs are now what is known as over-the-counter drugs. You can find them without a prescription in the drugstore. Some of these over-the-counter NSAIDs include things like acetylsalicylic acid. Another easier word for that is aspirin, and you can find that in generic form or in the brand name of Bayer's aspirin. The second drug we'll talk about is ibuprofen. That's again the generic term for Advil and Motrin. But the last one of the NSAIDs is naproxen, which is generic for Aleve. So first, let's talk about aspirin. As we see here, you can buy drugs you can always buy in generic form, which is going to be much cheaper than the brand name, but they are identical to each other. The one that's just more expensive is because of the promotion and then the advertisement that goes into it and the name recognition, right? So, but they do the exact same thing because they are exactly the same molecule. So let's first talk about aspirin. So a little bit facts to start our conversation here is that this is widely used medicine. 100 billion equivalent standard pills are consumed per year of this medicine. But it dates back way when. About 2,400 years ago, it has been established or has been documented that the Greeks would chew willow leaves to relieve the pain, right? That's how all medicine, or not all, but a lot of medicine have been discovered throughout the years, even before modern medicine came along, right? People just found things in nature, some kind of herb, some kind of animal, some kind of mineral that will heal whatever ailment they may have, but they may not even know what it is. But as long as they take that herb, they take that mineral, and they just feel better. So the Greeks have been shown to chew on willow leaves, and that relieves the pain. But that's where the modern science comes in. So more recently, it's been now isolated and more understood that the main ingredient for that pain relieving action is a compound known as salicylic acid. Okay, so this is the molecule of salicylic acid. So let's review our organic chemistry here. In this molecule, we have at the center here is the aromatic benzene ring. Offshoot of that is an alcohol group. Okay, an offshoot of another carbon there is Do you remember what functional group that was? That's the carboxylic acid group. Okay, so this molecule, salicylic acid, is called acid because of that carboxylic acid group. Okay, so now this was great, and it was used and experimented to, and is shown to relieve the pain and is anti-inflammatory. However, there were some pretty serious side effects to this molecule. The number one thing is that it causes bleeding in the stomach in the GI tract. So that wasn't good. So further research was made on it where they exchanged this alcohol group out and made it into an ester now. Now, with that addition of the ester or that transformation to become an ester, now this is called acetylsalicylic acid. That is the acetyl, this is known as the acetyl group. Right, so with this, the side effects have been lessened and the medication is more potent also. And so from that, we have the modern molecule known as aspirin. Okay, and it turns out, maybe some of you know, if you have some older folks in your family, that aspirin at its lower dosage is also prescribed to people who are prone to having a heart attack. It turns out it's because it has activity that prevents blood clot, which is a cause and correlation to heart attacks, right? So if you take a small amount of that, it does have this side effects. So these people who take it on an everyday basis, basically, at a small dose, though. Now, research is ongoing. Once they found aspirin, they wanted to find something a little bit more, even less with less side effects. So they did stumble upon this new drug called ibuprofen. Now, you may see ibuprofen just sold simple and generic form in like CVS, or you buy a whole bucket, a whole bottle of it from Costco, for example, or you can get it more expensively from Advil. Again, generic versus brand name, they do the same thing. Like as I mentioned, it was developed as a safer alternative to aspirin. However, it still causes some stomach issues for some people because of that carboxylic acid group it has there. It's, as you see, very similar. It also has that a benzene ring, but more hydrocarbons in the molecule. It does a very similar thing as aspirin, as in it reduces the fever, it can prevent blood clots and all that, relieves pain. But yes, it's mainly used for and reserved for alleviation of pain. So, like for example, I know some people who go on hikes and they will take ibuprofen to kind of help with that pain. Okay, so it's very strong for that. Now, the third and last of these NSAIDs is naproxen, and you may see it sold in the brand name of Aleve. Okay, now let's look at the molecule here. It is 2 aromatic rings. What functional group is this? This is the ether group. And then again, it has that carboxylic acid. So again, it's probably still has those side effects where it's not good if you have any stomach problems. Now, how is this different from the other 2 molecules? What makes naproxen stands out is its half-life. It has a much longer half-life than the other 2. It has a half-life of 12 hours. Remember the idea of half-life where we learned about it in nuclear chemistry? The time it takes for half of the molecule to go away, to disappear. In this case, the time it takes for half of the amount of the medicine to be cleared from your body, cleared from your system. So it takes a longer time for your body to clear Aleve, so then Aleve or naproxen can take effect longer times. So therefore, the dosage, the time it takes for you to take the medicine is also less. So compared to 4 to 6 hours with ibuprofen and aspirin, for naproxen, the dosage is between 8 to 12 hours. That's why it's advertised here as an all-day pain relief, because it lasts longer in your body, basically. But again, it does similar things. So before we talk about anything else, how do these NSAIDs relieve pain? Let's take a look at that. And I'm not gonna like, this is not a very a specific or major specific course, so I'm not gonna go into details about the biochemistry or the pharmacology of how the drugs works, just in a little bit of an overview, okay? So the simplest way to explain this is first you have an injury or some kind of causes of inflammation that occurs in your body. When that happens, um, this molecule known as arachidonic acid is released. So this used to be a part of the cell wall. Remember, the cell wall are fatty acids, and so they are this molecule is released from your cell wall, and with the help of various enzymes, it will then be converted. This acid is then converted into a molecule known as prostaglandins, um, particularly something called PGE2. Now, these molecules, the prostaglandins, their job is to then bind to receptors on nerve cells, and that's how it sends signals to your brain about the pain. Now, besides that, it's also useful to send inflammation signals to like elevate your temperature and send in help basically. So these are all signals to tell your body to heal itself. So it's actually needed, but also at the same time, it causes pain because it tells your body you're in danger, you're in pain. Right? So there's a whole cascade of molecules that happen here, but we don't need to know much about that other than the fact that at the end you have this molecule known as the pain, the pain chemical, and it's being converted from a molecule known as arachidonic acid with the help of various enzymes. Okay, so then how do the NSAIDs come in to save the day? Remember those enzymes I talked about? Well, they're called cyclooxygenase, or COX for short. So these are enzymes that are used to catalyze the production of that prostaglandins molecule. And then it turns out there are various types of COX. There are various types of cyclooxygenases. These enzymes, one is called COX-1. Their names are easy to kind of identify because there's just 1, 2, 3. Etc. So COX-1 is found in the stomach and in your kidney tissues, whereas COX-2 are found exactly where the inflammation is happening, where the pain, where the discomfort is coming from. Now, all the drugs we said here, all the NSAIDs, the aspirin, the ibuprofen, the naproxen, their job is to block both of these pathways. They block both COX enzymes, COX-1 and COX-2. Well, if the enzymes aren't there and they're being blocked, then they can't help produce prostaglandins. They can't produce that pain chemical to send out signals to your brain. Okay. But as a side effect, though, COX-1 is in turn, if you block that, it can lead to the side effects of excessive bleeding and stomach pain, which is prominent side effects of using NSAIDs. So that's why it's always a label for people who have bleeding issues or some stomach problems to not use NSAIDs. Or if you do, you don't use it for a long period of time because it will cause stomach problems. And also for children or for pregnant women, they're advised not to use it also. Now, so here comes in Tylenol. Okay, so the generic name for Tylenol is acetaminophen. So it turns out acetaminophen helps also reduce pain and fever, so it does the same thing as the NSAIDs, right? But it is not an anti-inflammatory and is not also an anticoagulant. Okay, and its mechanism of action is that it doesn't blocks COX-1 and COX-2 like the other three, where if you block COX-1, you cause that bleeding and that stomach issue, right? So in this case, it blocks COX-3 instead. So this enzyme, therefore, is not involved in that pathway that causes stomach issues. So because of that, acetaminophen is the most gentle of all these medicines in terms of stomach problems. So much so that it is the safest among all four as a painkiller for children and pregnant women, and also people with stomach issues. However, though, it still has its downsides, is that in fact it can cause liver and kidney damage if you use a large amount of it or if you abuse it with alcohol. It's getting too sunny for me there. All right, so that ends our discussion of the painkillers as the one type of medicine we found in our homes. So now let's move on to our next topic. So now I'm going to talk about soaps and detergent. So let's first talk about what is soap. So soap is basically this molecule here, where you have like a chain of hydrocarbons about like ranging from like maybe 15 to 17 carbons chains. Remember, hydrocarbons mean that every carbon is just filled up with hydrogens and is saturated here and with hydrogens. And on the other end, you have this carboxylic functional group that has been deprotonated. That means the hydrogen of the carboxylic acid group was taken out. So therefore now it is a negative charge because remember hydrogen is positively charged. If you take out one proton, you have this now negatively charged anion. So to balance that, we have sodium cation to balance out that molecule. That's what soap is essentially. And how is it made? It is made from ancient times to now by reacting animal fat or vegetable oil with what is known as lye, basically NaOH, which is a base. So basically, when you react animal fat, so any kind of vegetable oil with a base, you create this soap molecule. And so this was done even in a lot ancient times, or even in places where they have to make up their own soap, is that you get some kind of oil or just fat from the animal, and you mix it in with ash, even like pot ash or anything that you burn, because in that there are basic compounds. And so if you mix up with a batch of the oil with that base, over time, a reaction known as hydrolysis occurs that creates this molecule that is used as soap. Okay, so let's dig a little deeper into that vegetable oil. Remember, we've learned about this molecule already in a previous unit. This is called a triglyceride. Remember that it's basically three like carbon in a row, and each of those carbons are connected with an ester. Remember what an ester is? An ester is a CO double bond with an oxygen on one side also. So all of these have an ester, all of these carbons are connected to an ester. So that's why it's tri. These three esters, the important part about these esters is that it is a very long hydrocarbon chains at the other end, right? It could be 15 carbons like this one, 15 like this one, or 17 like that last one there, for example. Now, the word here is hydrolysis. So if you don't have ever heard of the word lysis, is to split something up. So hydro is water, right? So you're splitting something up with water, and having a base in there, an OH, a hydroxide, helps with this hydrolysis. It catalyzes this hydrolysis reaction. So you add an NaOH with water in there, it basically breaks this compounds up. It breaks it up where you have just this long chain here, and then you have this carboxylic acid chain. And then therefore this three carbon chain is like liberated, still connect to each other, but liberated from these longer fatty chains. So this is a byproduct known as glycerol. And then this, as it reacts with NaOH, becomes this soap molecule. Okay, so let's take a look further at how this soap molecule works. The primary feature of this molecule is that it has dual nature. It is both hydrophobic and hydrophilic. Remember what those words mean. Hydrophobic means afraid of water. What is afraid of water? Remember, water was polar. So what's afraid of polar? Non-polar. Okay, so this is the hydrophobic side because it only has carbon-carbon bonds and carbon-hydrogen bonds. Because of that, it is non-polar bonds. So because of that, that whole side is considered non-polar. So non-polar doesn't like to mix with things that are polar, like water. But it also has a full-on negative charge on one end of it. And that full-on negative charge is attracted to the water because remember, water has a positive side. The hydrogen is positive. So that negative side is now attracted to the water. And so that's why it's called hydrophilic. So that's called the polar head group, whereas this is the polar or the non-polar tail. Okay, so how is that feature makes how does that feature make this molecule very good as soap? They form something called a micelle. And so what a micelle is basically is that all of your tail end, which is very afraid of water, kind of clumps together in the center, leaving on the surface this negative charge, which likes the water, right? So basically you make a ball, a sphere, where all of your hydrocarbons, hydrophobic ends are in the center, and facing outside is the hydrophilic end. Now, how is that important? Well, it turns out the grime and grit and dirt you have on your body or in your clothes is all because of the impurities that then mix with the grease and oil, either from your food that you eat or from your own skin releasing or sweating out the oil. Because of that, when you want to wash your clothes or even wash your body with just simple water, because those things are now greasy, they can't just wash away with the water again because they're greasy, so they're hydrophobic, so they're afraid of water, so they won't mix with water. So if you just wash the water, it won't go away with the water. That's why you need the soap. The soap here can capture, because it has this center, like a safe space for greasy things, basically. So you have grease on your hands, grease on your clothes. These greasy clumps, molecules, then would travel into the center of the micelle, being protected because it is hydrophobic in there also. Now, because it has an outside sphere that is also hydrophilic, right? So water sees this whole ball and only see that hydrophilic side. So then that whole ball is also dissolved within the water. So you see how the duality happens here? The inside accommodates the hydrophobic grease, whereas the outside makes it being washable, being dissolved in the water. It won't precipitate out of the water. So because of that, when you wash, it captures the grease, but also flows away with the water because it is also soluble in the water because of that outside tail that is hydrophilic. Okay, so that's basically the premise of how all cleaning agent works. And that special name for such a structure is called a micelle. Now, there is a disadvantage of the traditional soap that I've been discussing, is that when you are in a place like California, we have something called hard water. Hard water just means it has, in addition to H2O, it has other minerals like calcium, magnesium, and iron. Because of this, it's called hard water. So what happens in hard water? It turns out these ions will react with the soap and precipitate it. Okay, so remember we said before that this molecule has a sodium, right? So when it's paired up, this anion here is paired up with the cation of sodium, it's quite soluble in water. However, if it pairs up with, if this negative side pairs up with calcium or iron, magnesium, that compound, that ionic compound, is no longer soluble. When it is not soluble, what happens? You get this crud, right? You see in your bathtub, you see it on your faucet, like this example here, of just this crud that's this kind of crusty buildup that's in your sink. If you may even see it as a ring on your bathtub or in your sink, and you have to clean periodically, right? So that's the disadvantage of the soaps because it does create that problem quite a lot. Now, we're not the only one who has that issue. Seen here in this picture here is a Roman aqueduct after 180 years of use. And you can see it has a very thick layer of that buildup, of that deposit over time. You see that? This, from here to here was the usual tunnel, right? But over time, this calcium or mineral buildup narrows it so much that you only have that much of like almost half or more than half is gone, right? So that's the disadvantage of using a soap because of if you have hard water. So now comes the development of detergents. So we try to solve that issue of having something that is insoluble and therefore build up in our sinks, in our tubs over time. So we have this molecule. It's like a soap. In many ways, it has a hydrophobic end and a hydrophilic end. So because of that, it can also form a micelle. So this is made up, the first kind of types of these detergents is made up of propylene. So remember these alkenes we saw in the organic chapter, benzene, so there's a benzene there, and sulfuric acid. And so that sulfuric acid is the side that makes the hydrophilic head because of the negative charge. Now, it turns out though, this polyatomic ion, you can call it, this anion, when paired up with like hard water minerals like calcium and such, will not will not precipitate out and cause crud and build up mineral deposits, basically. Because now we have this new hydrophilic subgroup. Now, there is a problem though. It is quite non-biodegradable. It is not biodegradable. So what happens when you use soap? There are these bacteria in the sewage system that kind of eats up and break down the molecule in the soap. It breaks down all the hydrocarbons and therefore kind of just gets rid of it, right? Or recycles it and it becomes something else. These branching though is what is different. Remember the other one was just kind of straight hydrocarbons. Now this has the branch. Because of that branching of the hydrocarbons, the usual bacteria that is at work cannot recognize this molecule and therefore does not break this molecule down. And over time, this builds up in the sewer system because as we use the detergent, it comes into our sewage system. The bacteria is not eating it up and therefore it still persists in nature. That's why it's called non-biodegradable. Now, this is a picture of the consequence of that taken in Fremont, California in 1972. You see all the buildup of that soapy foam, basically. So, as science does, when there's an issue, we can fix it by engineering a fix to it. And this is a biochemical engineering fix. So remember in the original soap, it was biodegradable because it had a linear chain instead of all this branching. But it had that hydrophilic head that that precipitates out. So why don't we combine the two features that work out? So that's what they actually did. They just kept the hydrophilic head that is soluble in water if bound with calcium and other minerals, but they made the hydrophobic end linear again. Okay, so let me show you. That was the original detergent, but with the branching, they just removed it and made it more straight, more linear, and that actually fixed the problem. The microorganisms, the bacteria then could recognize this new molecule and then eat it up, and therefore it is indeed biodegradable. And it still works, right? Because it still has that linear hydrophobic chain and that hydrophilic head to make a micelle to make it work just like soap. All right, so that ends our discussion of soaps, and also this whole lecture on household chemistry of the household items. So hopefully in your presentation, you can also talk about some other features, some other chemicals found in your home.